So today we are going to be finding absolute maximums and minimums, and then we'll be finding local maxes and local minimums using something called second derivative test. But let's get into the definition of what an absolute maximum is and an absolute minimum is. So for the first definition, it says if f of c is greater than or equal to f of x, this means is that if we have a y value at some x value of c, and this y value is greater than all the y values on the graph for all x in the domain, then this means that f of c is called the absolute maximum of f. It is the absolute highest point on the graph. Okay. Second definition says if f of c is less than or equal to f of x, this means we have a y value at some x value of c for all x in the domain of f that is the lowest, the absolute lowest or absolute smallest y value on the graph, then f of c is called the absolute minimum. So to show you a picture of what that means, I have these three pictures down below. And the second graph would be an example of an absolute maximum. This point here, which is going to be when y is 4 and x is 0, so this point 0, 4 would be considered the absolute maximum. It is the highest point on the graph. And then the third graph would represent an absolute minimum, the absolute lowest point on the graph, and this would be the point 0, 0. Okay. So to be an absolute max, you have to be the highest point on the graph, and an absolute min, you must be the lowest, absolute lowest point on the graph. And then for the first graph, this has no absolute max or minimum because we see that, yes, there's a high point here. Yes, there's a low point there. But since these tails go to infinity and negative infinity, there is no absolute high point. So these will just be considered local maximums and local minimums. Okay. So what we're going to look for today is an absolute max and an absolute min, or another way to say it is absolute extremum. Okay. And we come across our first theorem. It's called the extreme value theorem. A function that is continuous on some closed interval has both an absolute maximum and an absolute minimum on that interval. So if we take an open interval and we close it, this means that we cut off a continuous function. And if you cut off the function, then this means you will have an absolute high point and you will have an absolute low point. And the example of that are the graphs given below. So the first graph, we have a closed interval 2 to 12, which means we take this continuous function, we stop it at 2 and 12, which means if you have a closed interval, you'll have an absolute minimum, the absolute lowest point on the graph, and you'll have an absolute maximum, the absolute highest point on the graph. These points would be considered local maxes and local mins. Okay, so this is what happens on a closed interval. And the next three graphs are just like it. The second graph, we have a closed interval 4 to 10, which means we're using the same graph from before, but now we make the interval smaller. And now my absolute maximum changes. I now have an absolute maximum here and an absolute minimum there, only because we changed the interval. And then you change the interval up again. We change it to 4 and 8. Well, here the absolute maximum stays the same, but the absolute minimum is at 78. And then we change it one more time. We make it 3 to 11. And now I have two absolute maximums. I have an absolute maximum here at 105 and there at 105. And I get two absolute minimums at 73. Okay, so what this is telling us that on a closed interval, we can have multiple absolute maxes and absolute minimums. We just have to make sure that they are the absolute highest point and the absolute lowest point. Okay. Any questions on that? Nope. Okay. And theorem 2, so listen closely to this one. Theorem 2 says locating absolute extrema. Absolute extrema, or absolute maximums and minimums, must occur at critical numbers or at endpoints. So to find absolute extrema, we're going to be using critical numbers and the endpoints of a closed interval. So that line's really important. Okay, so let's go ahead and try it out. For example 1, it says find the absolute extrema of the function x cubed plus 3x squared minus 9x minus 7 on each of the following closed intervals, -6 to 4, -4 to 2, and -2 to 2. Okay, so first step is check to make sure our function is continuous. And once again, since this is business calculus, you will only be given polynomials, and every single polynomial is always continuous because its domain is always all real numbers. So that one's easy. Our domain is -infinity to infinity because we're given a polynomial. Okay. B, find the critical numbers in the interval. So this means that we are going to take the derivative of this function, set it equal to 0, and solve for x. Remember, that gives me critical numbers. Okay. So we'll say f prime of x, and we'll get 3x squared plus 6x minus 9. Okay. Now, after you take the derivative, you set it equal to 0. So let's go ahead and do that. F prime of x equals 0. 3x squared plus 6x minus 9 equals 0. Here I can factor out a 3, and I'll get x squared plus 2x minus 3 equal to 0. And then I'll factor it. I'll get 3 times x plus 3x minus 1 equal to 0. So that's x squared, -x, 3x. Good. And my critical numbers are going to be -3 and 1. We don't have to worry about that 3 in front. It doesn't matter to us. Okay, so there are my critical numbers. And now what we're going to do is find the absolute maximums and minimums on the given closed intervals above. So I have an XY chart for each separate interval. The first interval is going to be -6 and 4. Okay, and what we want to know when we list our values is, do the critical numbers we just found fit on this interval? So do -3 and 1 fit on the interval -6 and 4? Do they fit between those two numbers?
Yep.
Good. So since they do, when we make our chart, and I'll put them in numerical order, I'll have -6, which is my endpoint. I'll have -3, which is my critical number, 1 and 4. Now, let's say if they didn't fit, then I would not use them. That's as simple as that. If your critical numbers do not fit in the interval, then we don't use them. Okay, so now what we're going to do is take all these values and plug them into the original function. So lovely Desmos, always. Behind this, hide video panel, hide that, get that out of the way. Okay. So I'm going to type in the function we were given. X cubed plus 3x squared minus 9x minus 7. Do my table feature and type in those x values. Oh. I don't know why it does that. There we go. Okay. So -6, -3, 1, and 4. And there's my x value, my y values. We have at -61, 20, -12, and 69. Okay, now just look at your y values of this given chart and which one is the absolute lowest.
-61.
-61. This would be considered absolute minimum. And which is the absolute largest?
69.
69. That's our absolute max. Okay. Any questions on that process?
Nope.
Now we have two more intervals, -4, 2. So -4, 2. Do my critical numbers fit in this interval?
Yep.
Yep. So we do it again. So I have -4, -3, 1, 2. Well, we're plugging them into the same function. So we already know the values for our critical numbers, -3 and 1. That makes it easy. Oops. So -3 is 20 and 1 is -12. I need the value for 2. I see that down here. That's -5. And I need the value for -4, which gives me 13. Okay. Now looking at this chart, which is the absolute lowest?
-12, and the absolute max is 20.
Good. Absolute min, and then absolute max. All right, perfect. And then last is the interval -2, 2. Which critical number does not fit in that interval?
-3.
So we don't include it, we exclude it, and we only put 1 in there and 2. We already know the value at 1, which is -12. We know the value at 2, which is -5. Do we know the value at -2? 15. Okay. And what's absolute min? What's absolute max?
Min -12, max at 15.
Good. Okay. And that's how you find absolute maxes and mins. Any questions on that process?
Nope.
All right. So again, find the derivative, set equal to 0, get your critical points, see if your critical points fit in the intervals, and then plug them into the original function. And remember, the only reason we use endpoints and critical numbers, no other numbers, is because of that lovely theorem on the last page. It said absolute extrema must occur at critical numbers or endpoints. So that's all we use, endpoints and critical numbers. Okay. Next is the second derivative test for local extrema. So this test is for finding local maximums or minimums. So the reason this test is created is so that you can avoid a sign chart. This actually makes the process a lot faster depending on the actual derivative. So this says, let C be a critical number of f of x such that the derivative is 0, or the derivative at C is 0. Okay, number one, if the second derivative is positive at our critical number of C, this means that f of C is a local minimum. 2, if the second derivative is negative at our critical number, then f of C is a local maximum. Okay, so by this chart, this says that our critical numbers, of course, happen when you set the first derivative equal to 0. That's why that says 0. But for the second derivative test, this says that if the second derivative is positive at that critical number, this means that the original function will be concave up, which will create a local minimum. So your example would look something like this, and you would have a local minimum. Okay. And 2, it says, of course, your critical numbers mean your first derivative is equal to 0. And if the second derivative is negative at the critical number, then your graph will be concave down, meaning you'll have a local max. And remember, concave down looks like this. And you'll have a high point, which is your local max. Okay, well, let's say that, again, our critical point makes our derivative 0. And let's say that the second derivative becomes 0 at our critical number. Well, 0 is neither positive or negative, so 0 gives us no information. This means we have no idea what the concavity is, which means that this test does not apply. So if you fail the second derivative test, then you must make a sign chart. So not all shortcuts work all the time.
Ooh.
That's why my N looks like an H, the psi chart. Oh. Okay. All right, so let's go ahead and try this second derivative test out. Find the local maximums for the functions. Use the second derivative test to find your maximums or minimums. So first thing we're going to do is take the derivative of this function, set it equal to 0, and find the critical numbers. So let's get started with that. So we'll call this A. We're going to say f prime of x, which gives me 3x squared minus 12x plus 9. Set it equal to 0. And we get 3x squared minus 12x plus 9 equal to 0. Factor out a 3. And I get x squared minus 4x plus 3 equal to 0. And then factor this, and you'll get 3 times x minus 1 times x minus 3 equal to 0. Set these two terms equal to 0. Do not worry about the 3 in front. And we'll get that our critical numbers are x equals 1 and x equals 3. Okay. So now from here, we would normally go ahead and make a sign chart, but for this one, we are going to do the second derivative test. Okay. So this is going to be step B. All right. So B, second derivative test. So look at the first derivative and take the derivative of that. So we're going to say f double prime of x is going to give me 6x minus 12. So the way the second derivative test works is we're going to take our critical numbers and plug them into the second derivative. So I'll write that, of course. Plug critical numbers into f double prime of x. Okay. So we'll get f double prime of 1 and f double prime of 3. All right, we don't need a calculator for this. So you get 6 times 1 minus 12. 6 minus 12 gives me negative 6. And then 6 times 3 minus 12 gives me 18 minus 12, which gives me 6. So what this means by the second derivative test, for the first value, we see that the second derivative is negative at our critical number, which means the graph will be concave down and we'll have a local maximum. So this means that x equals 1 is a local max. Okay, and then for 3, we see that the derivative is positive. The second derivative is positive. So this will follow the first row of that chart above. Since the second derivative is positive, we're concave up, which creates a local minimum. So this means that x equals 3 is a local minimum. And there we go. And we have avoided a sign chart. Now, of course, if you wanted to find the exact location of these maximums and minimums, you know that you would take these points and plug them back into the original function. But I don't think we have to do that on this one. Okay, so this is what we're looking for. And that's it. The second derivative test helps you avoid a sign chart. Any questions on that page?
All good.
All right then. Well, that's it. We're done.